thanks everyone for give me and the Warwick opportunity to introduce to participate in this project, and also give an introduction about our work on the work package 2. Actually, this is under the work package 2 for the DIOR project, which is the channel modeling and also the impairments compensation in optical communication networks. So that's why I'm talking about one specific noise or distortions called equalization enhanced phase noise in the current long-haul nonlinear optical fiber communication systems. So this slide actually shows the researchers, investigators at Warwick's for the DIOR project, and we are working on, we have like me and Dr. Mark Leeson and Dr. Subhash. Then we are basically working on digital signal processing, system modeling, and for optical communication system and also various communication systems. We use intelligent signal processing techniques and including the machine learning techniques. We also, regarding the early stage researchers, we have around 10 PhD students and 1 research fellow involved in this DIOR project from Warwick's side. And basically for these works, I'm going to introduce the 4.0, the concept about the origin and the principle of the equalization enhanced phase noise, and what has been discussed and investigated for previous the linear communication system where the fiber linearity has not been considered, and also what is our current work about the equalization enhanced phase noise in the practical the linear long-haul optical communication systems. And then I will give some summary and acknowledgement to the researchers and support. So basically, so the left-hand side, the figure is a typical coherent, long-haul coherent optical communication system where we have this transmitter part. We add the information on top of the carriers from the transmitter laser. Then we feed the modulated signal into the fiber loop or into the cascaded fiber span. And after each fiber span, actually we have this optical amplifier. Then in the receiver side, then we use the coherent receiver. Then we mix the received signal and the locally generated the laser signal, and to get this coherent detection to implement the detection of the amplitude and the phase in the both the amplitude and the phase. Then we sample that using the digital analog to digital converter. Then we come into the digital signal processing part where we have the compensation of the dispersion, chromatic dispersion, and we have the compensation of laser phase noise, and then we use a filter to remove unwanted noise, and we estimate the signal quality. So the equalization enhanced phase noise means actually we have the interaction. If we look at the phase noise from the transmitter laser, it will go through the optical fiber and also dispersion compensation, the module in the DSP part. So the net dispersion experienced by the transmitter laser phase noise is close to 0 because this module can compensate the dispersion in the fiber. But if we look at the phase noise from the low oscillator laser, it will only go through, or it will go through the dispersion compensation module only. So in this case, there will be some interaction between the laser phase noise and the chromatic dispersion compensation module in the digital signal processing part. So some early works, from this the University of Melbourne and the Bell Labs, actually they realized this effect. They did some simulations and they found, okay, so if we remove the dispersion in the fiber by simulation, and okay, if we only have the phase noise, okay, we can see there is some impact as phase noise. If we remove the phase noise from this local oscillator part, but we keep the dispersion, so okay, we get ideal recovery of the signal. So, but if we have both the phase noise and the dispersion, okay, we see some additional distortion, but and also these distortions looks like amplitude distortion. So these distortion, I mean, is different from the traditional phase noise. So this is called equalization enhanced phase noise because it comes from the equalization of chromatic dispersion, and which is very important and key part for the dispersion compensation in current commercial coherent optical communication system. So all these works are based on simulation and I mean based on the linear communication system. They didn't consider any nonlinear fiber linearities. and also some basic models about estimation about these noise variance due to the EP and the equalization enhanced phase noise is estimated as this equation, and it increased with the dispersion coefficient, the fiber length, and also 3 dB length of the laser, and also decrease with the symbol rate, which means, decrease with the symbol period, which means it will increase with the symbol rate. So this is also different, quite different from the traditional analysis of the local oscillator laser. So, and also this effect is increased. I mean, if we increase the symbol rate or increase transmission distance, we see, okay, it becomes more and more significant. And also it will increase, I mean, the impact will increase with the modulation format order, the order of the modulation format. So these are earlier works and based on the linear communication systems where the people only focus on the impact of the origin of the equalization enhanced phase noise. And also, so previously when I discussed about this equalization, the generation of the equalization enhanced phase noise, okay, I mentioned that dispersion compensation module is in the post, I mean, in the digital signal processing part in the receiver side. So this is called post compensation of the chromatic dispersion, where the equalization enhanced phase noise scales with the 3 dB length of the local oscillator laser. That is because the net dispersion experienced by the local oscillator laser is not narrow, it's quite significant. So, but if we have some pre-compensation of the chromatic dispersion, if we move the chromatic dispersion in the transmitter part, so we do some pre-compensation, so we can see, okay, the laser phase noise will not experience actually the chromatic dispersion because the data will interact with the chromatic dispersion. So the laser phase noise will go through the optical fiber dispersion only, and the local oscillator laser phase noise will experience no dispersion because there is no dispersion compensation module. So in the receiver part. So in this case, we will see or predict or conclude that there will be interaction between the transmitter laser phase noise and the fiber dispersion. So in this case, okay, the EP arises from the transmitter laser and the fiber dispersion. So previously, that's all the early works about all the analysis of this origin of the equalization enhanced phase noise in linear system. We have been involved in some of that work. So, but inside, I mean, within this DIOR project, and we start to consider, I mean, the joint effect between the chromatic dispersion, the laser phase noise, and the fiber linearities. Because for long haul communication system, we need to currently people actually increase the modulation format order, and also which requires the high transmission power, and also if we increase the number of the number of transmitted channels or the transmission bandwidth, we also need high power, where the fiber linearity cannot be neglected and is quite considerable. So in that case, so the first work actually we just discussed, I mean, the impact of the equalization enhanced phase noise in the nonlinear optical communication system when we have this multi-channel transmission and also the multi-channel nonlinearity compensation, which means, okay, we have 9-channel transmissions in the forward propagation. This work is based on also the simulation where we have this 9-channel, the forward propagation in the fiber, and also we do the digital backpropagation, the fiber nonlinearity compensation with 1-channel, 5-channel, and 9 channels, which means, okay, we just compensate a small portion of the fiber nonlinearity or larger portion of the fiber nonlinearity or the whole portion of the fiber nonlinearity. So in this case, we can see the impact of the equalization enhanced phase noise actually becomes larger and larger for if we increase the compensation part. If we have this 1-channel compensation, 5-channel compensation, and 9-channel compensation, actually the impact of the EPN actually becomes larger. And also when we change the different modulation format, and also the impact will become larger when we evaluate the performance of the beta rate. And then we went into actually the detailed or theoretical analysis of the system model considering the equalization enhanced phase noise. So here, here in the fiber nonlinearity, so in the fiber, we consider the fiber nonlinearities. Then the signal to noise ratio was, I mean, according to this Gaussian noise model, the signal to noise ratio and the receiver side can be evaluated as a ratio between the transmitted power and the noise from the amplifiers and the fiber nonlinearities, and the interaction between the signal and the noise interaction. So where this fiber nonlinearity interference can be expressed as this one, it increases with the number of channels and the effect length and symbol rate, yeah, and also the signal power. So then if we want to include the impact of the equalization enhanced phase noise, we need to consider additional term that these equalization enhanced phase noise actually will also interact, I mean, scales proportional to the, I mean, launched signal. I mean, that's why we have this term that's a product between the equalization enhanced phase noise and the signal power. And also there will be a further interaction between the signal and the equalization enhanced phase noise. This one is actually, that's the impact of the equalization enhanced phase noise is equivalent to the impact of the transceiver noise. I mean, it limits the system performance in terms of the signal to noise ratio, not just the distortions, which means if we further increase the signal power, the impact of equalization enhanced phase noise will increase proportionally. So it will limit the upper signal to noise ratio. Then there will also be the interaction between the signal and the local oscillator, the equalization enhanced phase noise. That's actually due to the propagation of the signal inside the fiber, because the EPN actually is produced between the phase noise and the fiber dispersion. Like if we take this phase noise from the local oscillator side as an example, okay, when we have this nonlinearity compensation, then the phase noise will interact with the dispersion compensation module, and at the same time, so this will produce some EPN. So within the first virtual span for the compensation, but this EPN will interact with the signal in terms of this mixed nonlinearity. This behavior actually will produce additional interaction term. So that's why we have this term in the Chen model. So then we compare our predicted model and the numerical simulation based on the split step Fourier transform split step, Fourier transform solution of the optical fiber. So we can see actually our model, can give a good prediction on the system performance when we considering the equalization enhanced phase noise. And this is 5-channel. And also based on this work, and if we further increase the transmission distance, we can see actually the equalization enhanced phase noise becomes more and more important. And also for these blue lines shows, and the dots actually shows this solid line actually shows if we don't consider the impact of the equalization enhanced phase noise, and these dotted lines, or dashed lines shows actually if we consider the impact of the equalization enhanced phase noise, and I think we can see actually the impact is quite considerable. That's almost 2 dB or 1.5 dB. Yeah, and also if we look at the beta rate, this European effect will decrease, will degrade the performance of the beta rate for different modulation format. So this one is 16 QAM, this is 64 QAM. And also for the multi-channel system previously, so we studied previously, the study was in the multi-channel system, but we only look at the central channel, the performance of the central channel. But if we look at the performance of different channels, so an interesting phenomenon shows that the performance of the central channel gives the best performance compared to the side channels or outer channels. So this is actually shows the equalization enhanced phase noise put more significant degradation on outer channels when they have the full or huge bandwidth linearity compensation. So this actually is different, or actually exactly reverse as the previous analysis of the digital either digital backpropagation or any other digital linearity compensation. We don't consider the impact of equalization enhanced phase noise. That is because previously, generally we believe the central channel gets the most significant impact in due to the linearity, because it has neighboring channels, but for outer channels, it only, the left-hand side, it only have the channels in the one side. So it will be influenced by less significant by the fiber linearities compared to the central channel. But for the phase noise, we can see, okay, for actually it gives stronger impact for the side channels. So this assumption, okay, actually is based on if we do a full field dispersion compensation or digital backpropagation or the linearity compensation based this linearity compensation techniques. So because sometimes if we want to do a full field or full bandwidth compensation, we need to capture all the informations over here. We take example of 9 channels transmission. So we need to do a simultaneous compensation over the all compensated bandwidth channels. That is because when we are doing this compensation, so this shows the phase profile of the chromatic dispersion in either the chromatic dispersion or the linearity compensation. So if we have the same frequency fluctuation for the central channel, okay, the produced phase fluctuation is smaller, but for outer channels, when we have the same bandwidth fluctuation, it will produce larger phase variation in the dispersion compensation profile. So we believe that's the origin of this effect becomes stronger for outer channels. Yeah, so basically that's all of our work. Current work under the work package 2 for this DIOR project. And regarding the channel modeling and next step, we are doing the second train to doing the second part is this compensation of this equalization enhanced phase noise. So, but for this channel modeling work, we realized that this equalization enhanced phase noise can play an important role in the long haul systems and need to be considered in the system performance evaluation and system modeling. And these are our PhD students involved in this project. And also this project is we have this, I mean, currently this is supported by DIOR and also the UK National Grid project.